Okay, so today we're going to be starting chapter 14, VectorValued Functions. VectorValued Functions. Okay. So, we spent all this time talking about vectors. Now we're going to talk about functions whose outputs are vectors. Right? So it's a function that takes in a number, right? Takes in a real number, and returns a vector. Okay. So basically this course is a little bit odd, but so it's this course is in multivariable calculus, right? Multivariable calculus, right? And the constructs that have several variables are vectors, right? When they talk about multivariables, it really means that you're dealing with vectors. But it's sort of like, it's almost as if we don't believe that you can handle it all at once. And so the text is arranged like this. Say, well, we're going to look at outputs that are multivariable, but the inputs are single variable first. Okay. And then, so that's part one of the course. Part two of the course, well, still we don't want to go all the way. We look at functions whose inputs are multivariable, but the outputs are single variable. Okay. And then after that, we say, okay, finally we're going to look at functions whose inputs are multivariable and whose outputs are multivariable also. Okay. So that's really where you want to be, and in some sense it's a little bit strange to do these halfway steps, which take up a large amount of the course, but each of them has its own flavor, and in fact lead to different sorts of theories. Okay, so it's not completely useless to do this. Yeah. Okay. So so now we're in part one of the course. Okay. So vector value functions. Definition, as you might expect. A vector value function is just a function with vectors as its values. Vector value function is a map f going from R to R3, usually denoted with a vector sign over it because the thing that it spits out is a vector. And usually the notation is like this. T goes to f1t, f2t, f3t. Where f1, f2, f3, the fi, are functions from R to R. Are called component functions. Okay. So, just to make sure that this makes sense, right? So this guy here is a vector valued function. These guys here are scalar valued functions. Okay, right? Because these are the coordinates. They should be numbers, right? You're not going to have vector valued outputs within the vector. That would be like a vector of vectors. Okay, I mean, you can do something like that, but we're not going to, right? I mean, why would you? Okay, so for example, let me make this concrete. For example, you could have this guy here. F of t is saying cosine t, sine t, t. F of t is cosine t sine t, comma t. Okay. Right. So at time 0, that thing is going to be at 1, 0, 0. Right? The thing is going to be at 1, 1, 0, 0. Right? It gives this vector, right? And then say at time pi over 2, where is it? Well, it's going to be at this is x and this is 1. at time pi over 2, well, it's going to be at 0, 1, pi over 2. Right? So it's going to be over here, at pi over 2 up. And then if you just look at the first two coordinates, as time progresses, you see that if this were in the plane, then this would just be the output would be vectors that spun around the unit circle. Right? You all see that? Right? The output's going to be just vectors whose terminal points lie on the unit circle and advancing counterclockwise. Right? In this case, we're in 3 dimensions, and our z coordinate is the same as our time. So it's the same thing. It's simply that your point is not only spinning around, but also rising at a speed directly proportional to the time. Okay, so you get it's a helix, right? You get this helix. It's going to spin around the cylinder x squared plus y squared equals 1, right? And go upwards like this, and then go downwards as time reverses. Right. So this thing here is x squared plus y squared equals 1. Right. It's on that circular cylinder, x squared plus y squared equals 1, and just winding around it. Okay. So I guess to be proper, I should draw it as a bunch of vectors. Right. So it's going to be the outputs are these vectors whose endpoints are at those points. Okay. So you also have this other term, parametric curve, which is almost exactly the same thing. So a parametric curve in R3 is a map of the form f of t is f1t, f2t, f3t. Okay. I almost want to erase this immediately. In fact, I probably will. It's just, you think it's just a vector value function, but you don't think of it as a vector, just as the point. Okay, so it's what I had up initially, before I put all these vector marks on it. Right? You just think, right? Instead of thinking of this thing as a vector, you think of it as a point, right? And it's just this. You think of a point walking around like this as time goes on, rather than vectors whose endpoints are at that point. But people tend to basically mix the two things up because they're basically the same thing. So in this course, we will conflate them just like everybody does. See, these are exactly the same thing, right? If sometimes if I say like the vector ABC, well, what I mean, and I've written up a point. Really, I mean the vector whose end goes from 0 to ABC, whatever. Okay. Okay. Here is an example from the text. It says, give a parametric description of the intersection of the cylinder x squared plus y squared equals 1 with the plane y plus c equals 2. Okay, so the picture you have in your head, right, is one, you have the cylinder, right? The cylinder is going up and down, right? X squared plus y squared is equal to 1, right? And then you have this plane, say this is y and this is z, right? So z equals 2 minus y, so it goes like this. right? You have this plane that sort of hard to see it, but in the zy plane, it's this line, right? So here in the zy plane, it's this line that goes like this. Okay, and then you just take copies of it and slide it along the x-axis. Okay, so it makes this plane like that. Okay, so basically you're cutting a plane through the cylinder, right? And you end up with some sort of elliptical thing. Okay, right? You have a tube and you slice it, right? You end up with an ellipse. Okay, and one way that you could describe it is as follows. You could say, well, look, I know that x squared plus y squared equals 1. So I'm just going to use the parametrization that I have over there, right? So I'm going to take x and y. I'm going to describe x and y like this, right? So gamma of t will be, this will ensure that it lies on the cylinder, right? This will ensure that, having this will ensure that x squared plus y squared equals 1. We're lying on the cylinder, and we're walking around it, right? And then we want to ensure that y plus z is equal to 2, right? Well, here's my y, so I know what my z is, right? Z is going to be 2 minus my y. 2 minus my y, right? And this would give you a description, right? As t goes around, this thing spins around and at the right heights. So this is an example of a of a parametric description of this object in space. Okay. Okay. But in any case, the point is that we're dealing with functions whose outputs are vectors or are positions in space. Okay. So right. So what we want to do first, yes,
Okay.
Yeah.
So how do you find the actual ellipse? Isn't it a specific? How is it not a specific ellipse that you're trying to find in that picture? Like, how come the answer is like that and not a specific ellipse?
You mean you'd like to write it as you'd prefer to write it as like some in x's and y's and like a sort of like a that you have an ellipse in space.
Yeah.
Yeah. You could, but this is the question is simply to give a parametric description of it. That is to make a function whose outputs describe the image, make a function whose image is exactly this thing. Okay, and that's actually simpler than the question that you want to answer.
I'm just wondering why they want that and not the actual.
Maybe because it's easier to do this.
Okay.
and maybe it's actually more profitable to be able to do this than to do what you're suggesting.
Okay.
Yeah, like this is actually maybe more useful than being able to tell what ellipse this actually is. To express the ellipse in the other form. Yeah. Okay. Yeah. And I guess most relevantly, this is an example of a vector value function. Okay. So just like you did in single variable calculus, we're going to do the things that matter: limits, continuity, differentiability, etc. Right? What do these things mean in the vector valued sense? Okay. So we're going to reconstruct the basic ideas. Okay, so let's recall first. What does it mean? So back in single variable calculus, right, what does the limit of f of x being L as x approaches C mean? What does that mean? The limit of f of x is L as x approaches C. What does that mean to, there are several ways of talking about this. I'm kind of curious what you all have seen before. What does it mean? Nothing. Does it mean anything? You've seen it before? You've seen it before, but you immediately erased it from your memories as a bad experience. What does it mean? You can tell me anything. You can all sorts of things. Yeah, Alana.
It's when it's approaching C instead of not necessarily right at the point C. So the limit is where the function is approaching.
Okay, so this means that as x approaches C, f of x approaches this number L. Right? Okay. Anybody have anything else other than that? Lily.
The derivative at x equals c is L of f of x?
Not necessarily. Not necessarily. So right now we're just talking about limits. If it were something like this, if we said that the limit of f of x plus h minus f of x over h as h approaches 0 equal L, then that would mean that the derivative existed and that the derivative was L. Okay. So it's not the same. But right now, we're not looking at a slope of a secant line or anything like that. We're just looking at the value. We're just looking at a function itself. Anybody else? Anything else? Has anybody seen the epsilon delta definition of limit? Some of you. Melissa's nodding. Great. Okay. So there's this thing called the epsilon delta definition. Epsilon delta definition. Right. It says, right. So here's your. Here is L, say. Right. And here is, let's say. Let's see. Get to. Here's C. And I'm going to even let it pass through that. Okay. Doesn't have to, but I'm going to let it pass through for the picture. Okay. So, right, for the limit to be L means that, you know, as your x values get close to C, as your inputs get close to C, your outputs get close to L, right? One states that there's a way of stating that very precisely. There's a way that is proved most useful. Okay, there's a way of stating this in a very useful way, in a very useful manner. Okay, and it's as follows. You say, given any epsilon distance to L, there is an interval of radius delta about, so let me say like this. There's an interval about C in which the outputs lie within that distance, within epsilon of L. Okay, and the key is this word any. Okay. Given any distance, given any epsilon distance to L, there's an interval where the outputs lie within that distance of L. Okay, this turns out to be the best way to define the limit. Okay, let me try to explain what this means. Okay, so here's something that we say, you know, should have a limit of L, right? Right. As you get closer to C, the outputs get closer to L. Okay. So you notice what happens if somebody demands that the outputs stay within here of, say, within 1. So it says I'm going to demand that the outputs stay within 1 of L. Well, I can find an interval about C in which the outputs satisfy that, right? I can find an interval about C in which the outputs satisfy that. Okay, and notice if somebody says, I'd like you to stay within 1/4 of L, well, I can find an interval in which the outputs satisfy that. And if somebody says, I'd like you to stay within 1/1000000000 of L, you can find an interval in which the outputs satisfy that, right? Given any distance here, looking at this picture, given any distance here, there's an interval in which given any tolerance here, right, machine tolerance, right, there's an interval in which that tolerance is satisfied. Okay, and this turns out to be the right way of explaining what limit means. Okay, so it's this thing that mathematicians call the limit of f of x is L. Okay, given any epsilon distance to L, there's an interval about C, and really we say a punctured interval because we don't care what happens at C itself. So we don't really care what happens in the middle. Okay, there's a punctured interval about C in which all the outputs satisfy the tolerance. Okay? And so this is written in mathematical language like this: given any epsilon greater than 0, there exists a distance, say a radius, delta greater than 0, such that if all points in C minus delta, C plus delta, excluding C itself, then f of x, the distance of f of x to L is less than person. Okay, so this is the actual definition, which is fine. I'm putting quotes around it. This is the actual definition. If you go in math, then it will become important. In this course, it's not so important, but I feel like you ought to have seen, you should see it, because this is what turned out to be the right way to define the limit. Okay. Yeah, the most fruitful way of defining the limit. Okay, so okay, so yeah, so just out of curiosity, so what do you think the limit should mean? What should this mean? The limit of f of t is L as t approaches t naught. If we're trying to switch everything over to the vector valued world, what should the definition be? What should the new definition be? Peter?
Could it be the limit of each of the components at t as they approach t naught?
Okay, so that's possible, right? You could say maybe it means that the limit of f1 is L1, the limit of f2 is L2, and the limit of f3 is L3. Right? Maybe that's the way to do it. That limit, for the limit of a vector value function to be some vector, means that each component must attain the limit, have in it as its limit the component of the vector. Right? Anybody have other ideas? One could try to do something along the lines of the epsilon delta. Again, out of curiosity, what does continuity mean? So what does f continuous at c? What does f continuous at c mean? What does it mean for a function to be continuous? Yeah, Alana.
I think it means the limit from the right and the left is equal to the point at like, the output of the function.
So, right, the limit of the function as x approaches c is actually the value of the function, right? Which is equivalent to what you said, that right and left limits turn out to be the same thing and equal the value of the function. So this is one way that one defines continuity, right? That the function doesn't surprise you, right? As you're heading towards it, you're expecting a certain limit, and when you get to that point, you actually have that limit. Okay. So like it doesn't. You have a limit, and when you get there, it's the function value is what you thought it was. So it's sort of like predictability. Your function is not surprising at that point. Right, and so again, you could ask like, what should be the vector valued? What should be the vector valued definition? What should be the vector valued definition? Well, yeah, and similarly, you talk about what does differentiability mean? Right, we mentioned earlier, right? F prime is c, so f differentiable at c means that the limit of f of c plus h minus f of c over h as h approaches 0 exists, right? And that so you ask, we'll need to answer what it means to be differentiable for a vector value function. It turns out, and this is sort of a cop-out. Is this common language these days? Cop-out? Do you still use this phrase? It's kind of old-fashioned. How about jip? Do you say jip? What a jip? No? Okay. So you might think that you're being gypped by what I'm about to say, so the author. So let me say it this way: it's possible to do everything from the epsilon delta point of view. The author, like many authors, takes sort of an easier way, which is to do everything component-wise. So this is it's equivalent. It turns out to be, if you think about it, it turns out to be the same thing, but to a mathematician, sort of unsatisfying. Okay, so basically, the definitions that we use are all going to be component-wise extensions of the one variable definitions. Okay? So the semi-easy way out. So here's how we're going to define limit. We say that the limit of this thing is L as t approaches c. So you have a vector valued function, and as t approaches c, we say that the limit is L. L is, of course, L1, L2, L3. We say the limit is L if, component-wise, your one variable limits are L1, L2, and L3. As t approaches c. In other words, the vector limit holds if and only if the scalar limit holds. Scalar limits hold for in each component. Okay, and similarly for continuity, we're just going to say, we say f is continuous at c if the limit of f of t is f of c, right? If the function's behavior at c is predictable. In other words, if the limit of fi t is fi c as t approaches c for I equals 1, 2, 3. So it boils down to being continuous component-wise. Okay. So we say that you're continuous if each of your components is continuous. I.e., if each component function is continuous at C. Okay. So for example, if we look at the helix, right, f of t is cosine t sine t t. Okay. Is f continuous at t equals 0? Is this function continuous? So what does this boil down to? You just look at the definition, you say, okay, we're asking if the limit, right? If the limit is the limit of each component function equal to, is the limit of this thing equal to f at time 0 as t approaches 0, right? F at time 0, of course, is going to be 1, 0, 0. Right? So all we're asking is so R, the limit of the first guy, 1 as t approaches 0, the limit of the second guy, 0 as t approaches 0, and the limit of the third guy, 0 as t approaches 0. Right? So we're just asking component-wise, right? In each component, does the limit of the component function equal to the value of the function, the value of the corresponding component function? What is it? What does it? Yes. Okay. So verifying continuity, is just as simple as in the one variable case. It's equally simple. Okay. So yeah, so it may seem like calculus 3 is simply you do calculus 1 3 times, which I'm afraid is the case for now. Yeah. Okay. So yeah, so that we might as well have introduced stuff back in calculus 1 in some sense. In fact, that's the trend in across the U.S. They're starting to merge calculus 1 with calculus 3. Yeah, my cousin who had her education in Taiwan had never heard of single variable calculus. She said, "What is a single variable calculus?" Because they had never learned they had learned it as multivariable calculus from the very beginning. Okay. So nothing that fancy. Let's go on. Okay. 14.2. Derivatives and antiderivatives. Derivatives and antiderivatives. Okay, so recall that the derivative of a one-variable function is, of course, the limit as h goes to 0 of f of t plus h minus f of t over h as h tends to 0. Right? So this is one variable. Right. And the geometric interpretation, you recall, is that you have this function, right? So here is t, and you're looking at t plus h, right? So f of t plus h, you get some height, and you subtract off f of t, right? You get this f of t plus h minus f of t, right? And then you divide by h, which is this thing here. So you get this divided by this, right? And that gives you the slope of this line, right? That gives you the slope of this line. So the slope here is f of t plus h minus f of t over h, right? That's the slope of that line. And then you let h go to 0, right? And so you end up with the limit of the slopes of these secant lines as the second point, as the second point tends towards the first point. Right? So t is the slope of the tangent line, the limit of the slopes of secant lines, aka the slope of the tangent line. Okay, so for the vector value case, you do the same thing. F, a vector value function, then f prime t is defined to be the limit of f of t plus h minus f of t over h as h goes to 0. Okay. If this limit exists, right? If this exists, it's called the derivative of f at t. Okay. So let me ask you, what is this? What is this thing? is this, I'm going to ask you something simple. Is this a number? Is this a vector? What is it? What is it? Well, you've got a vector, right? This thing is a vector, right? And you're subtracting off another vector, right? So far it's just a difference of vectors, which is a vector, right? And then you divide by some number, right? So you're taking your vector and then you're scaling it by some number, right? 1 over h, right? So what is it? It's a vector, right? It's another vector, right? And sort of pictorially, right? If you're, right? So you have something like this, right? Your here's t plus h, right? And then you're going to have f of t, right? F of t plus h. Right? So maybe here's f of t and f of t plus h, right? So you take that difference, right? You remember what the difference looks like, right? So it's going to be a thing you add on to t to get there, right? So it's going to look like this, right? It's going to be pointing towards the second guy. Is my picture too awful? So you have something like this, right? Here's f of t. Here's f of t plus h, right? And then this guy here is your difference, right? F of t plus h minus f of t. Right? So you have the difference is going to be this vector going from the second guy to the first guy, right? From the second guy to the first guy, and then you divide by h, right? Okay, and then you take the limit as h goes to 0, right? So as h goes to 0, this thing is going to head backwards towards f of t, right? And you see what you get. You get this vector. You get this vector that's going to be pointing. It's going to be pointing tangent to the curve that f was walking. Okay. Do you all see that? Right. So right. So it turns out to be this vector. It's called the f prime t is a vector also called the tangent vector. The tangent vector to the curve at f of t. Right? Because you have this curve that's described by your function. Right? And you're going to end up with some vector that is perpendicular to the curve, tangent to the curve. Let me make the picture a little bit better. So maybe the origin is here. Say. Okay. So the vector you get is going to be perpendicular to the curve. Okay, not necessarily perpendicular to this vector, but perpendicular to the curve here. Okay. So this derivative vector, right? This derivative vector has this geometric interpretation. And what it turns out to be is the following. Theorem. If f of t is f1t, f2t, f3t, a vector valued function with differentiable component functions, then it turns out that the derivative is sort of as you expect, the vector whose components are the derivatives of the component functions. So f1 prime t, f2 prime t, f3 prime t. Okay, so going back to our example of the helix, right? F of t was cosine t sine t t, right? The tangent vector is going to be, of course, negative sine t cosine t, comma 1. It's going to be this vector. Right? Turns out that this function is different. This vector value function is differentiable, and its derivative is going to be the vector-wise, the component-wise, the derivative of the original function. Okay. So maybe I'll explain more about that next time. Okay. So let's stop here for today. Let me pass back some homework and at the same time ask if you have any questions. I think it's all pretty straightforward. It turns out that everything in the vector value case is just done component-wise from the just done component-wise. No.